In this lesson, we're going to take a look at the physics definition of work. And when we say work in our everyday life, what we usually mean is the job that we do to earn money. But in physics, work means something different. In physics, work is actually what happens when a force acts through a distance. And so we're going to have to calculate it, and we're going to have to keep track of the direction of the force compared to the distance through which it acts. So in the activity you guys did, you looked at 3 different scenarios where work may or may not have been done. And what we come up with is we come up with the physics definition of work, which is an equation. We say work is equal to the magnitude of force times the magnitude of displacement times the cosine of the angle between them. So this angle is measured between the force and the displacement. Okay? Now we're going to look at an example where we do a little bit of work where the force in motion might be in opposite directions, might be in the same direction, or might be at some weird angle in between. But it's worth pointing out that because the cosine is included in this, work can be positive, work can be negative. And when we get into energy, we're going to try to understand what it means to do positive work and what it means to do negative work. But for now, let's think about why we can have positive and negative work. A cosine curve, if you recall, starts up here at 1, and in one complete cycle goes to -1, and then back up to 1. So this is 180 degrees, and so that's -1. So that tells us that when our force and our displacement are in exact opposition, right? So if my displacement's this way, 180 degrees from that is this way, that means I'm going to have a -1 value, which means my work is going to be negative when the force and the displacement are in opposite directions. If the force and the angle have no degrees of separation between them, that is, they're in the same direction, then of course the work is going to be positive because we have a cosine of 0 is 1. And if we're somewhere in between, then we're going to have positive or negative work, but only a part of the force is actually doing work. So it's only the part of the force that's in the same direction of the displacement that does work, or if we've got work opposite the displacement, that does negative work. So let's take a look at, say, a box being pulled by a rope. So I've got tension pulling the rope or the box that way, and I'm going to have friction acting that way. And we're going to have this thing moving at a constant speed. So speed is constant, and we'll let the coefficient of kinetic friction be 0.3, and we'll let the mass of the box be 10 kilograms. And what I want to know is how much work is done by tension, and how much work is done by friction, and while we're at it, how about work done by gravity, or work done by the normal force. Okay? So those are the 4 things we're going to look at. So let's go ahead and label those other 2 forces. I do have the force due to gravity pulling down and the normal force pushing up. Now it's not accelerating in any direction at all, which of course means we can write Newton's second law in the y direction. Net force in y equals Fn minus Fg, and that will be 0, which tells us Fn equals Fg, which equals mg. And so this, of course, is 10 times 9.8, which is 98 newtons. Now, good, now I have the force, so I can calculate the work done by normal force or gravity. Well, if it's moving at a constant velocity along that incline, the displacement is that way, the forces are either that way or that way. Either way, that's going to be 98 newtons times, let's say it moves 10 meters, and then the cosine of 90 degrees. Well, the cosine of 90 degrees is right here on my cosine curve, and right there is 0. So the work done by gravity is 0. There is no work done by gravity, which kind of makes sense because this thing hasn't changed in terms of its position relative to the ground. It can't fall to the ground. It hasn't been driven into the ground. Gravity and the normal force balanced each other and did no work. So is that what we're going to see when we also do the tension force and the kinetic frictional force? Well, not quite. because the displacement is going to be in the same way. So if we find the work done by tension, that would be the tension force times the displacement, and I just said let's make that 10 meters, times the cosine of the angle between them, cosine theta. And so for this, if it moved 10 meters in the direction of the tension force, then I would have whatever my tension force is to make this thing move at a constant rate. Well, if the coefficient of friction is 0.3, that means Fk equals Fn times the coefficient of friction, which would be mg times the coefficient of friction, which would be 10 times 9.8 times 0.3. So this would be 29.4 newtons. So I have 29.4, because these two forces balance, right? It's not accelerating. 29.4 times 10 times the cosine of 0, because it is moving in the same direction as the tension force. So the angle between the tension and the displacement is 0, which the cosine of 0 is 1. So this is 294. 294 what? Well, we took newtons times meters times the cosine of an angle. That's just a number, it doesn't have a unit. So this is Newton times meters. But that is important enough that it gets its own name. Work is measured in joules. So a Newton meter is actually a kilogram meter per second squared times a meter, which is a kilogram meter squared per second squared. That's equal to a joule. We use a capital J. It's named for James Prescott Joule. So if we refer to the unit, we use a lowercase j when we write it out. Otherwise, it's the proper noun, we're talking about the person. But we do have joules of work. So this is 294 joules. That's how much work was done by the tension force in dragging that box along the floor. However, friction did the exact opposite amount of work. So the work done by the frictional force is equal to the kinetic frictional force times the displacement times the cosine of the angle between them. Well, the angle between the displacement and friction is 180, right? If it's moving 10 meters to the right and friction is to the left, then what I have is the 29.4 newtons times the 10 meters times the cosine of 180. And that is negative 294 joules, which means the total work done by all of the forces when we add them up is 0. 0 work done by gravity and the normal force because they're perpendicular to the displacement, so they can't do work, and 0 work done by the combination of tension and kinetic friction because those two cancel each other. However, what's interesting about that is if you're the person pulling the rope, you did 294 joules of work against friction, which did negative 294 joules of work. So no work was actually done on the box, but whoever was exerting the force was doing work. Now, if this was something a little bit different, where we took and we put this force instead of at a parallel to our motion, if this force was at an angle, then our angle of motion, I guess, then our angle that we use here would not be 0, our angle would be whatever that is. But it would be the cosine of that angle, which would be the x component of that force, which is the component of the force that's in line with the displacement. So really, what we do when we find work is we find how much force is in the same direction as motion, and we use that to calculate work.